According to the National Electrical Code, for a 480 volts 3-phase 436 amps load, best practice is to use 3 separate conduits, one for each phase or line to line. For 350 kcmil conductors, you can run 1 conductor per phase in each of the 3 conduits for a total of 3 conduits. You could consider 2 conductors per phase and 2 conduits for a total of only 2 conduits. However, it is generally not recommended to run 2 conductors per phase and 1 conduit because it can be challenging to pull 4 large conductors, specifically 2 phase conductors plus 2 neutral conductors, into a single conduit. Multiple conductors in a conduit can generate more heat, which can reduce the current carrying capacity of the wires. The National Electrical Code requires each phase to be in a separate conduit. For a 480 volts 3-phase 436 amps load, it is often best to use 3 separate conduits, each with 1 350 kcmil conductor per phase. This will help ensure compliance with the National Electrical Code and provide a safer and more reliable installation. Consider the impact of conduit fill on conductor ampacity. The National Electrical Code addresses this in Article 310.15 Cone, which covers adjustment factors for more than 3 current carrying conductors in a raceway or cable. When the number of current carrying conductors in a raceway or cable exceeds 3, the allowable ampacity of each conductor must be reduced. This rating is necessary to prevent overheating due to the combined heat generated by the conductors. The adjustment factors are specified in Table 310.15 Cone of the National Electrical Code. These factors vary based on the number of conductors. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity must be reduced to 80% of its original value. If there are 7 to 9 conductors, the ampacity must be reduced to 70%. These adjustment factors are cumulative, meaning that if other conditions also require rating, such as high ambient temperature, those factors must also be applied. Ambient temperature correction factors are addressed in 310.15b. High ambient temperatures can also reduce the ampacity of conductors. Conductors are typically rated for a specific maximum operating temperature, such as 75 degrees Celsius or 90 degrees Celsius. When the ambient temperature exceeds the temperature rating of the conductor, the ampacity must be reduced to prevent overheating. The correction factors for ambient temperature are provided in tables associated with 310.15b in the National Electrical Code. These factors are applied in addition to any adjustment factors for the number of conductors. For example, if a conductor has an allowable ampacity of 100 amps at an ambient temperature of 30 degrees Celsius, but the ambient temperature is 40 degrees Celsius, the ampacity must be reduced by multiplying it by the appropriate correction factor from the table. Consider voltage drop calculations. Voltage drop is a critical factor in electrical system design because excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Voltage drop can be calculated using formulas that take into account the conductor length, current, and impedance. These calculations help ensure that the voltage of the load is within an acceptable range. The formula for voltage drop in a single-phase circuit is voltage drop equals 2 times the current times the length times the impedance divided by 1000. For a 3-phase circuit, the formula is voltage drop equals the square root of 3 times the current times the length times the impedance divided by 1000. Where current is in amps, length is in feet, and impedance is in ohms per 1000 feet. Consider conduit sizing calculations. Proper conduit sizing is essential to ensure that conductors can be installed and maintained safely and efficiently. The National Electrical Code specifies the maximum allowable fill for conduits, which is typically 40% for 3 or more conductors. To determine the appropriate conduit size, you must calculate the total cross-sectional area of all conductors and compare it to the allowable fill area of the conduit. Chapter 9, Note 9 of the National Electrical Code provides the dimensions of different types of conductors and conduits. The conduit fill calculation involves summing the cross-sectional areas of all conductors, including insulation, and comparing that total to the maximum allowable fill area for the conduit size being considered. For example, if you have 350 kcmil conductors, you would look up the cross-sectional area of a 350 kcmil conductor in the National Electrical Code tables, multiply that by 3, and then choose a conduit size that has an allowable fill area greater than that total. The National Electrical Code specifies different types of conductors based on their insulation material and temperature rating. Common types of conductors include THHN, THWN, and XHHW. THHN conductors are typically used for dry locations and have a temperature rating of 90 degrees Celsius. THWN conductors are suitable for wet locations and also have a temperature rating of 75 degrees Celsius. XHHW conductors are cross-linked polyethylene insulated wires that are suitable for both wet and dry locations and have a temperature rating of 90 degrees Celsius. The choice of conductor type depends on the specific application and environmental conditions. Each type of conductor has different properties in terms of ampacity, temperature rating, and suitability for wet or dry locations. Selecting the correct type of conductor is critical for ensuring the safety and reliability of the electrical system. The National Electrical Code provides tables that list the allowable ampacities for different types of conductors based on their size and temperature rating. These tables are essential for determining the appropriate conductor size for a given load. The ampacity of a conductor is the maximum amount of current that it can carry continuously without exceeding its temperature rating. The ampacity of a conductor is affected by factors such as the conductor material, size, insulation type, and ambient temperature. The National Electrical Code tables provide ampacity values for conductors in various conditions, allowing you to select the appropriate conductor size for your specific application. Consider short-circuit current rating. The short-circuit current rating of electrical equipment is the maximum amount of fault current that the equipment can safely withstand. It is essential to select equipment with a short-circuit current rating that is equal to or greater than the available fault current at the point of installation. If the short-circuit current rating of the equipment is too low, it can fail catastrophically during a fault, leading to equipment damage, fire, or injury. The available fault current is the amount of current that would flow during a short-circuit condition. This can be calculated based on the utility source impedance and the transformer impedance. Electrical engineers use software and calculation methods to determine the available fault current at various points in the electrical system. Equipment such as circuit breakers, fuses, and switchgear must have a short-circuit current rating that is sufficient to withstand the available fault current at their location. The National Electrical Code requires that all electrical equipment be marked with its short-circuit current rating. This information is essential for ensuring that the equipment is properly applied and protected. When selecting equipment, it is important to consider the coordination between different protective devices such as circuit breakers and fuses. Coordination ensures that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Protective device coordination studies are performed to determine the optimal settings for circuit breakers and fuses to achieve proper coordination. These studies take into account the time current characteristics of the devices and the available fault current at different points in the system. Consider grounding and bonding requirements. Grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing protective devices to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. The National Electrical Code specifies detailed requirements for grounding and bonding. These requirements cover everything from the size of grounding conductors to the methods for bonding metal enclosures. The grounding electrode system typically consists of a ground rod, metal water pipe, or concrete encased electrode. The grounding electrode conductor connects the grounding electrode to the electrical system. Bonding conductors are used to connect metal enclosures, conduits, and other non-current carrying metal parts to the grounding system. The National Electrical Code requires that all metal parts that are likely to become energized be bonded to the grounding system. This helps to prevent electric shock by ensuring that there is no voltage difference between different metal parts. Consider the use of overcurrent protection. Overcurrent protection devices such as circuit breakers and fuses are essential for protecting electrical circuits and equipment from damage due to overloads and short circuits. Circuit breakers are automatic switches that trip and open the circuit when an overcurrent condition is detected. Fuses are one-time use devices that melt and open the circuit when an overcurrent condition occurs. The National Electrical Code specifies the requirements for overcurrent protection. These requirements cover the selection, installation, and coordination of overcurrent protective devices. Circuit breakers and fuses are selected based on the ampacity of the circuit and the type of equipment being protected. The National Electrical Code provides tables that list the maximum allowable overcurrent protection for different types of conductors and equipment. Coordination between different overcurrent protective devices is essential to ensure that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Selective coordination is a design approach that ensures that only the overcurrent device closest to the fault operates, while other upstream devices remain closed. This is achieved by carefully selecting and setting the time current characteristics of the overcurrent devices. Consider the importance of arc flash hazard analysis. Arc flash is a dangerous phenomenon that can occur when there is a fault in electrical equipment. An arc flash can generate intense heat, pressure waves, and toxic gases, which can cause serious injuries or even death. An arc flash hazard analysis is a study that is performed to determine the potential arc flash hazards in an electrical system. The analysis involves calculating the incident energy and arc flash boundary at various points in the system. Incident energy is the amount of energy that a worker would be exposed to during an arc flash event. The arc flash boundary is the distance from the arc flash source at which a worker would be exposed to a hazardous level of incident energy. The results of the arc flash hazard analysis are used to determine the appropriate personal protective equipment, or PPE, that workers must wear when working on or near energized electrical equipment. The National Electrical Code requires that employers provide arc flash training to their employees and ensure that they wear the appropriate PPE. Arc flash PPE typically includes flame-resistant clothing, gloves, face shields, and helmets. The incident energy levels are typically expressed in calories per square centimeter. The higher the incident energy, the more protective the PPE that is required.